It's a pleasure to introduce Anubhav Mukherjee from Princeton, and Anubhav will talk about exotic embeddings of submanifolds in formula.
Okay, thank you very much for this great opportunity, and today I'll be talking about these sort of exotic embeddings of submanifolds in 4 dimensions. So, as some of you might be familiar, that 4 dimensions sort of turn out to be the smallest dimension where the difference between smooth category and topological category occurred. So notation wise, I'll call a property exotic if it is true in the topological category but not in the smooth category. So sort of remarkably, what happened is that the techniques that sort of works in lower dimension, which sort of help us to go between topological category to smooth category, such as various nice tools from dynamics such as Ricci flow stuffs, or even in the higher dimension, surgery theory, for some mysterious reason, they all kind of failed in dimension 4. And just to get an idea how crazy dimension 4 is, here is an interesting theorem. Friedman, Donaldson, Taubes, maybe many more. I'm not able to track every single person, but it's saying that the Euclidean space Rn has unique smooth structure if and only if n is not equal to 4. And R4 has uncountably many I would say exotic smooth structure. That means that those as a smooth manifold, they are all homeomorphic, but none of them are diffeomorphic to each other. Also, here is a interesting problem, is that 4-dimensional smooth Poincare conjecture, which is still sort of very much unknown, says that whether 4 sphere has unique smooth structure or not. Okay, so this is about smooth structure, but in this talk, I'll mostly talking about embeddings. So for this talk, I will assume X is simply connected manifold. Until I mention otherwise, I always assume that I'm talking inside simply connected 4-manifold. So since I'm talking inside simply connected 4-manifold and I'm interested in embeddings of subspaces, you can automatically see that I'm not anymore interested in how 1-dimensional space sits inside a simply connected 4-manifold because of this codimension reason. They all are kind of smoothly isotopic to each other.
Will X always be closed?
So I'll mention that. Maybe sometimes I'll assume it closed, sometimes I assume it compact or open. But at least all the time, even if I don't mention, I'll assume it to be simply connected. Okay, so So the interesting object of embedding would be then the surfaces and three manifolds. So let's say definition that we call a pair of let's say manifold y1, y2. Here they could be either surfaces or three manifolds. In four manifold X to be exotically embedded if there exists a topological ambient isotopy taking y1 to y2, but no such smooth isotopy exists. So to us, this is the notion of exotic embedding, when if there is a topological way to move one surface or a three manifold into another copy, but we cannot really do it smoothly. Okay. So before stating my main result, I would like to mention another mysterious phenomena that sort of happened in 4 dimensions. So in 1960s, Wall discovered this phenomena that exotic behavior in dimension 4 is very unstable. And what does that mean? That means that let's say you have some exotic property P inside some 4 manifold X. If you stabilize this 4 manifold, and by meaning of stabilization is that you connected some with copies of S2 cross S2s with this 4 manifold X, and then you push this property inside this bigger 4 manifold, then what happens is that this exoticness disappears. That means if you have an exotic smooth structure on a 4 manifold X, if you connected some bunch of S2 cross S2, eventually those 2 4 manifold actually now become diffeomorphic. Similarly, for surfaces, later in this result improved by Perrin and Quinn, that if you have pair of exotic surfaces inside a 4 manifold, if you do connected some that 4 manifold with S2s cross S2s, then also those surfaces eventually become smoothly isotopic.
So since this is a colloquium, it would be a really good idea to state the theorem that Wall actually proved, so that people have something they learned, right?
Oh, okay.
It's a specific statement.
So
X is closed, simply connected.
So the theorem that Wall proved that in 1960s, that 2 closed simply connected four manifold X and X prime, which are homeomorphic, becomes diffeomorphic after connected sum with finitely many. S2 cross S2s. and
The
later.
statement was more effective. It was really on the level of listing invariants, where people didn't know at the time. It was well before Friedman, so they didn't know that that was a complete set of homeomorphism invariants. He just said, suppose the intersection forms are the
Yeah,
are equivalent.
yeah, that's right. Okay, so with this idea in mind, then one could ask this following question: is that given an exotic phenomena, what is the minimum number of
And is that kind of phenomenon, the singular is open, phenomenon is plural. It's okay. Open.
this?
Yeah.
What is the minimum number of stabilizations one could need?
Can I ask a dumb question?
Sure.
As a non-topologist, why does one think to stabilize by S2 cross S2
So
or something else?
So this is sort of comes in a natural setup because two non-diffeomorphic but homeomorphic manifolds sort of fits inside a nice cobordism structure which is known as H cobordism. And the middle level of this cobordism, so this is sort of the 2-4 manifold X1 and X2 that are homeomorphic but non-diffeomorphic. They kind of fit inside this nice 5-dimensional cobordism, and this cobordism can be built only using 2-dimensional 5-handle and 3-dimensional 5-handle. And so the boundary, this is the common boundary of 2 handles and 3 handles, and this is where the copies of S2 cross S2s arrive. And since they are gluing along the common boundary, that means they are now diffeomorphic. So that's the reason this mysterious object sort of arrived here. Okay, so what I would like to say now that at least till 2021, almost all the examples of exotic phenomena that we knew has this property that those exotic phenomena become smoothly equivalent after connected sum with a single copy of S2 cross S2. So this is sort of something very interesting that happened, is that most of the example that in 4-dimensional topology people figure out till almost 2021, they has this interesting property as well that you can, with some brute force, can actually construct by adding another S2 cross S2. You can prove that they now become smoothly equivalent. So there is this sort of question that kind of give you an indication, automatic natural question, that is one stabilization sufficient. So
When you say those, do you mean exotic structures or do you mean exotic embeddings?
I mean that almost all this, so including exotic structures and exotic embeddings. So every kind of exotic examples that came up till around that time all kind of satisfy this property.
Will you speak about this in more details? What happened really?
After this?
Yeah.
Oh, yeah, I'll explain my work now.
Who did this? It's your work.
Yeah,
right?
so.
So in these theorems, the number of S2 times S2s that you need is usually not actually concretely calculable, right? It's
At this point, yes. Maybe in future, we don't know. So of course, like this is a basic question, or one could propose is then that is a single stabilization.
a single sum in.
Yeah, single S2 cross S2 is enough. Okay, so now I'll talk about my work about stabilization for surfaces. So now let's for a moment focus the submanifold as surfaces, and in the very end I'll also talk about my work about three-manifolds. So first I'll be talking about exotic surfaces in four manifolds and stabilization. So as I says that I was very vague here when I said that most of these phenomena kind of died after you connected some one copies of S2 cross S2. So let me tell you a concrete result that is true for surfaces. So this is sort of using David Gabai's four-dimensional light bulb theorem. There's a group of people, so Oakley, Melvin, Oakley, Kim, Melvin, Ruberman, and Hannah Schwartz. They prove in 2018 that a pair of exotic surfaces, exotic connected surfaces in a closed for manifold, or in fact this is true for manifold with boundary also. So let's say in a compact manifold. Oops. Yeah. Compact simply connected for manifold. And these are surfaces, so they represent some element in the second homology. So we need some more conditions on how these surfaces, or what are the elements they represent in the second homology. So which represent non-characteristic element in second homology become and their complements are simply connected. Become smoothly isotopic in X connected sum S2 cross S2. And so this is the precise statement that how exotic surfaces can become smoothly isotopic after a single stabilization. And as I said, that in most of the examples that's been proven before this result kind of falls under this category. So that means that almost all these examples of smooth surfaces then automatically become smoothly isotopic after you connected some copy of S2 cross S2.
What's a non-characteristic element?
So that is so this is sort of the homological restriction. That means x square congruent to 0 mod 2. Okay.
You're just saying that the reduction mod 2 is not the second Stephen-Whitney class?
Yes.
Or in other words, in terms of Wu relation. But
Yeah.
What about divisibility of the classes?
Sorry?
Does it take into account if the classes or the surfaces are different in terms of divisibility of the classes?
Sorry.
Classes, homology classes realized by the surfaces must be divisible by the same natural numbers or not?
they are in the same class, and his definition is that they are ambiently, topologically homeomorphic, so they're in the same homology class.
They're isotopic.
They're ambiently isotopic,
Yeah.
but in the topological category.
But
So they're in
then-
the same, they're in the same homology.
But then why this about characteristic elements?
No, no.
Question about the reduction mod 2 of the class, whether it's W2 or not.
Ah, okay.
Okay. So thank you for asking the questions. So yeah, so you could see now that even if I try to answer, I try to propose a negative answer of this question, I have to come up with a new kind of example of an exotic structure. But there is another problem, not only coming up with a new example, but another difficulty is that, how about an invariant?
What is the light bulb theorem that this refers to?
So light bulb's theorem says that if you have two homologous spheres, actually you don't need sphere, but you need any surface with sort of the simply connected complement, and if it has a common dual, then actually they become smoothly isotopic inside the four manifold, in a simply connected four manifold.
Common dual, what does that mean?
So common dual means there is another sphere which is transversally geometrically intersecting at one point to the surface. So the second point, the second difficulty in answering this question is that how about coming up with an invariant? So what invariant could be useful? So, because the point is that, so one way I have to construct something, but then I have to use some tool to say that, okay, they are topologically equivalent, but for certain reason, they are not smoothly equivalent. So in some way, then I have to compute an invariant which gives us different values for those two surfaces. So the classic invariant that has been used till, let's say, 2021 are sort of Donaldson's invariant, Seiberg-Witten invariant, let's say Heeger-Floor, so the interesting fact is that all these invariant vanish in a four manifold which is of the form X connected sum S2 cross S2. This invariant vanishes. And this is sort of, by using sort of neck stretching or adjunction inequality, you could prove that this kind of invariant vanishes. So we have to think of how we can cleverly use an invariant which still be sensitive when you connected sum S2 cross S2. And this is the point when this using of diffeomorphism came to my mind. So that instead of using this regular invariant, maybe I could now use a parameterized version of this invariant. And that is where diffeomorphism comes to the picture. So I'll sketch a proof, but let me state the result, that theorem. This is joint work with Zhangfang Lin and myself, where we are able to prove that there exists a pair of surface sigma comma sigma prime inside a punctured K3. So that means you take a 4 ball out from the K3 that are topologically isotopic relative to the boundary, but not smoothly isotopic. And they remain non-smoothly isotopic in K3 connected sum S2 plus S2. Okay, so before I sketch a proof, anyone has any question regarding the statement?
There was one S2 cross S2.
Yes, so I could only, that's right, that I could only handle so far only one S2 cross S2.
Is it important that you remove the point?
Yes, this is important, yes. You could.
It's like 2 or 3.
Huh? I what?
You know the numbers.
I know 19 S2 cross S2 can make it smoothly isotopic. You can see. Oh no, I'm not going to that part. This is more complicated. But if you are interested, I could explicitly show you how 19 could work. But.
What is the genus of the surfaces?
Yeah, I'll draw. Yes, sorry. I'll draw the picture.
It's related to what? It's topologically isomorphic related to what?
Oh, related to, sorry, my bad. Boundary. Okay.
So these are surfaces with boundary in your picture?
Yes. Yeah, that's yeah. So I'll kind of draw the picture. So
They're not closed surfaces?
no, they are not close. I mean, in recently, like this year, I proved actually closed surfaces. This result for closed surfaces as well. But I'll not talk about that. I'll just talk about this result for now.
So this is similar, the kind of type of result by Gary Booth that does something similar?
No, Gary does internal stabilization. So he does internal stabilization. So
Internal. I
yeah.
see.
So this guy doesn't appear at all. So there is more freedom to use invariant because all the gauge theory that appear in K3 can still be useful in his examples. But the point you are now here, everything sort of like disappear because of this adjunction or reason.
There was a lot of activity in this. Try to understand exotic, try to understand stabilizations being, but the question that I asked, there's some other result about exotic surfaces.
Yeah, he kind of in his title he put that name stabilization, but later I think I chatted with him and now he changed the name. Yeah.
Handle into the surface,
Yeah.
and then the invariance that you have can still see the difference. And in your case, the
Yeah.
invariance vanishing.
Yeah. So yeah, I talked to him, and now they use another definition, which is called internal stabilization, just so that people don't get confused.
In other words, you don't stabilize the four-manifold, you stabilize the surface. That's the difference.
Yes. Yeah, he does that. Yes. And in fact, as I say, I recently even constructed an example that doesn't that remains exotic after all kind of operations. So, but I'll not talk about all those. But you could like see my archive post recently. I in fact I prove a result which is satisfy his example and like my criteria as well. Okay, so sketch. So it's important, as some of you pointed out, that it's important there's a punctured, or moreover, like it's not only punctured, but I actually like take 4 ball out and then compactify it. So it's a manifold with boundary, whose boundary is the 3 sphere. So I could take a neighborhood of this boundary, which is nothing but S3 cross I. Okay. Now I have an interesting diffeomorphisms on 3 spheres. So because of Hatcher's proof on Smale conjecture, we have a very good understanding of now what is orientation preserving diffeomorphism this group looks like. And in particular, we know that pi 1 of this is, so this is homotopic to SO4. So this is Z mod 2Z. So in particular, there is an interesting non-trivial loop, gamma. So let's consider this as the non-trivial loop of diffeomorphism, which is based on identity. So this non-trivial loop of diffeomorphism can actually gives you a diffeomorphism, let's call it delta, on S3 cross I, and delta restricted on this boundary is identity. And now using this delta, I could construct a diffeomorphism on that K3, punctured K3, as extending this delta as identity on the complement. So let me draw some pictures. So this is my S3 cross I. And I kind of put the K3 on top of that, and I have my dent twist here. So we can think of this is sort of the generalized version of dent twist. So I have my dent twist here, and I extended everything by identity. So let's call this is my diffeomorphism, delta from punctured K3 to punctured K3. Okay. So now my goal is to use this diffeomorphism to construct some interesting pair of exotic surfaces. So let's recall how in a topological way we could construct a punctured K3. That is, we start with S3 cross I, and then we attach a few 2 handles. And if you're not sure what is 2 handle, you could think of that it's sort of boundary of a 2 skeleton. And then you cap it with a 4 ball. So this is how we could construct a K3 surface. Okay, so I could extend this attaching region to this bottom boundary, and let's call sigma be the disjoint union of all this core of these 2 handles. So be all this disjoint union of 2 handles. So this is my first candidate of surface. These are the, or let's say, core of the 2 handles. Okay. And now I want to construct sigma prime, and of course I have my exotic diffeomorphism here now. So I kind of have this exotic I have this interesting dent twist here, kind of like twisting this S3 cross I neighborhood here. So I could apply that on my sigma and define sigma prime as delta of sigma. Okay, so my claim now is that
How is this sort of been twist in this S3 course now?
sorry.
Is that an actual dent twist, or what exactly is this twist?
So yeah, this is an actual dent twist. Like in annulus, this is how we construct dent twist, right?
But what's the angle exactly? This is S3?
Yeah, so annulus is S1 cross I.
Right.
You can think of this is S3 cross I. In annulus, then you take
High dimensional annulus.
yeah, this is hard one.
Explain to everybody how it works on the annulus and how it works here. That
Oh, so
see what a dentist is.
so in annulus, the way dent twist works, like pictorially, it sort of send this arc to this arc, but you could think of that an annulus is sort of S1 cross I, and each of these S1 fiber, when you varies the time, induced a self-diffeomorphism, right? So this diffeomorphism can then be represented as a element of pi1 of diff of S1. And this group is Z, so that's why there are every twist sort of represented by the Z many ways. But in S3 cross I, if we just generalize this definition, then since this group becomes Z mod 2, so there is only one such choice, non-trivial choice.
Okay, so right, you can do only one. You
Yeah.
do it again, you
Yeah,
do it.
if you do it again, it becomes trivial. So my claim is that now sigma and sigma prime are exotic, but actually I'll prove that they remain exotic in punctured K3 connected sum S2 cross S2. Okay, so first of all, let's prove that they are topologically isotopic. And this part follows the fact, so this is sort of a proof result by Orson, Powell, and Kranich, Coopers. So they proved that dent twist on the boundary S3 of a punctured simply connected four-manifold is topologically isotopic to identity relative to the boundary. So they already proved that this dent twist itself is always topologically isotopic to boundary, and since these two surfaces are joined, sigma prime is defined by image of sigma with respect to delta, so we can use that, we can precisely use this topological isotopy to prove, make these two surfaces topologically isotopic. So now the complicated part is sort of proof that these are not smoothly isotopic. I mean, if I prove that they are, so this is a general result for any simply connected four-manifold, a punctured four-manifold. If you consider that boundary dent twist, then that is topologically isotopic to identity relative to boundary. So it doesn't matter which way you are. Okay, so now the smooth isotopy. So I'll prove it by contradiction. So let's for a moment assume that sigma and sigma prime are smoothly isotopic. So this is sort of proof by contradiction. Smoothly isotopic. If these two surfaces are smoothly isotopic, then I can further use this smooth isotopy. So using this isotopy, I can assume that the diffeomorphism that I constructed on punctured K3, delta restricted on sigma is pointwise fixed. Because if those two surfaces are isotopic, I could just further use that isotopy to assume this fact. Okay. So now let's notice that the neighborhood of sigma is nothing but a disk bundle with fiber disk, right? Because it's a two-dimensional disk, the core, and it's 4 dimensions. So the neighborhood is nothing but a disk bundle over disk. So in particular, I can further smooth isotope so that I could assume that in the neighborhood, this map on punctured K3 is even like the fiber preserving. So in fact, with further smooth isotopy, make it fiber preserving. Okay, so this is now fiber preserving. So that means this diffeomorphism will, in this neighborhood, be determined by a map which is mapping each of these base point corresponding the fiber is a diffeomorphisms now. So in this neighborhood, this map will be captured by this homotopic information, which is just a map from D2 to diff plus D2. But notice that this restriction of this map on the boundary is still identity, right? Because if I just be in K3, I'm just adding a 4 ball here. So, and everything is sort of extended by identity, and everything is happening now in this region. So here I still have identity. So
is it true that sigma has a lot of components?
yeah, but they all are kind of disjoint from each other.
So what's the map from the neighborhood to D2?
Sorry.
What's the vertical map from the
So this is, I'm saying that the neighborhood is a fiber bundle over D2 with fiber D2.
What's the map?
Is this like on one component of?
Yeah, so each
It's a disjoint union.
Yeah. This sort of disjoint union. No? Yeah.
So sigma is actually just a disjoint union of disks abstractly.
Yeah. And now, delta restricted on boundary of this is identity. So that means this information is captured by pi 2 of diff plus of D2. But we have a very good understanding of what is diff plus of D2. This is nothing but pi 2 of SO2, and this is this is same as a circle, so this is trivial. So that saying that I could, because of this fact, I could even say that delta is now actually identity on n of sigma. Okay. So pictorially, let's think what we did. So I'm drawing now in a side way. So we had K3, and we have our den twist here, which was supported on S3 cross I. But we are able to prove that if sigma and sigma primes are smoothly isotopic, then this den twist relative to boundary is smoothly isotopic to a diffeomorphism which is identity on everywhere except possibly in this disk, in this 4-ball. Okay? And so now let's add our S2 cross S2 also in the picture. So if I add an S2 cross S2 here, then this S2 cross S2 I could think of having here similar to here. So this whole analysis is essentially telling us that on punctured K3 connected some S2 cross S2, delta is now smoothly isotopic to a map which looks like now identity on the K3 component, and I really do not know what map, but it is some diffeomorphism on this part which is nothing but, let's say, the S2 cross S2 part. And now I want to prove that this is not possible. If I prove that this is not possible, then that proving that this assumption was wrong. So, but now gauge theory, sort of the family version of gauge theory that I want to use is only defined for closed 4-manifold, but you can see that this is a manifold with boundary. How could I make it close? I could add another copy of K3 here.
Same orientation?
Yes. I just add another copy of K3. So, K3. Similarly, I have another copy of K3. So now whole point boils down to, so now what I'll do is that I'll compute this invariant called family into equivariant family Bauer Furuta invariant. So this is sort of, I'm not going to define this because I do not have time to define this, but this is invariant that takes consideration of the homotopy type of the Seiberg-Witten map. And I'll consider the Pinto equivariant of that map. So F stands for family, B for Bauer, F for Furuta, Pinto. And we able to compute the corresponding invariant for this map and this map in this setup. So for this manifold, we construct, let's say, delta connected some identity on S2 cross S2. And if we plug in this information inside this invariant, we can prove that this is non-trivial. But if I put this second information, that is diffeomorphism, which is now identity on K3 connected some K3, and some diffeomorphism F, which is only now supported on S2 cross S2, this invariant is still trivial. And because of that difference, that concludes that these two diffeomorphisms as a diffeomorphism are not smoothly isotopic, which implies now these two surfaces are not even smoothly isotopic even after you connected some of S2 cross S2. And as I said that, I do not know what happened in the case if I connected some another S2 cross S2, because in that situation, both these maps disappear. So I cannot really conclude anything. But you could see that if you know a little bit about the construction of K3, now there are sort of 22 copies of disk here, and we even in our paper we show that actually if we make 19 S2 cross S2 connected some there, you can actually control the smooth isotopy and make these two pairs smoothly isotopic. So this is the story about surfaces. So now last 10.
Can I ask you this? So this invariant, what is it invariant under? Like you have these two maps that.
So you have a parameterized Seiberg-Witten map. Now so this is very technical, but I'm
not worried about the definition at all. Okay. Just like what is it invariant under? Like you have this map F and G. Like that have different invariants. What
That means then they are not smoothly isotopic. If they give you different invariant, that means they are not smoothly isotopic. And this whole analysis saying that this map delta connected some identity on S2 cross S2 is smoothly isotopic to identity map on K3 connected some K3 connected some diffeomorphism here. And this invariant now giving different values for these two diffeomorphisms. So that means these two diffeomorphisms can never be smoothly isotopic.
So the family of maps involved is the isotopic? Is that
Yes, yes.
So it's just the one parameter family
Yes,
of maps?
yes. And that is where this theory came handy, as I says that usually the regular invariant like Seiberg-Witten or Donaldson or Bauer-Furuta, those invariant vanish when you connected some S2 cross S2, but we consider a parameterized version. In the parameterized version, they may not vanish. And that is what happening here. So this is one.
Parameterized one would be fine for K3, connecting some K3, but when you throw in the S2 times S2, if you didn't have the family version,
then this vanishes as well. Yeah, that's right. Thank you. Okay, so this is about surface. Now the story becomes a little more trickier when we go to three manifolds. So now let's talk about three manifolds in four manifolds.
color might work.
Sorry. Three manifolds in four manifolds. Now, for surfaces, there are more techniques that are available which can say that when two surfaces are at least topologically isotopic inside ambient four manifold. The problem is that no such result known for if you consider three manifold inside four manifold. So handling topological isotopy is in fact problem. And maybe for that reason, I would like to mention the new results, not new, but relatively new results that have been proven along this line by Watanabe and similarly independently by Burdney and Gabay. They proved that there exist two different embeddings of three balls inside S1 cross B3 that are not smoothly isotopic but homotopic. And at this point, they do not know if they are topologically isotopic or not. In fact, Gabay told me that actually he can now prove that they are not even topological isotopic. So this is the so for that reason they called such examples as knotted embedding because they are really not exotic in a sense. So knotted embedding. So then the question is that how do we construct exotic embeddings of three manifolds in four manifold? And then again, I thought about maybe the problem is handling topological isotopy, but I know a cheating technique to use to bypass that technique if I just use instead diffeomorphism and look at a three manifold and its image under a diffeomorphism. And using that result, actually we are able to prove the first example of exotic embeddings of three manifold in four manifold. So towards the beginning of 2022, I am able to prove this with Ida, Kono, myself, Taniguchi. So a simpler version of our result saying that there exist infinitely many exotic copies of 3-sphere in this fixed manifold, which is 4 CP2 connected sum 22 CP2 bar. So we prove many more generalized version of this result in our paper, but probably this is the simplest way of explaining to the audience that we can able to prove that there exist infinitely many 3 spheres that are sitting inside this 4 manifold. But then you could ask in the same fashion that how does connected sum of S2 cross S2 behaves under this. In fact, we are able to prove, and which is actually true for both of these examples, that these examples actually becomes, oh sorry, not red, smoothly isotopic after connected sum with a single S2 cross S2. Okay, and I'll end it with one of my latest result, and unfortunately I do not have any time to give a proof, but I remember I gave a talk here like a couple of months back when I talked about this result. So theorem. So again, this is the simplest version of the result. This is by Kono, myself, and Aniguchi, where we showed that there exist 2 copies, Y1 and Y2, embedded in 2 S2 cross S2 that are topologically isotopic but not smoothly, and they are not smoothly isotopic in 2S2 cross S2 connected sum M, where M is any connected 4 manifold. So this is one of our latest results where we could now prove that not only S2 cross S2, but you can connect any 4 manifold, connected 4 manifold with S2 cross S2, but the examples that we constructed remain still exotic. And I would like to propose one last question, actually, is that...
There's a connected sum of a large number of copies of S2 times S2. Doesn't that sort of...
So you are right that if, instead of M connected, if we allow this to be disconnected, then we are able to stabilize. But if we assume M to be connected, then we cannot make it. So there is 2 ways of you can think of connecting S2 cross S2. Since let's say these are the 2 copies, pictorially, if you connect all the S2 cross S2 on the one side, they still remain exotic. But being disconnected means then you have freedom to then do connected sum wherever you want, and that can make them smoothly isotopic. But otherwise, in this category, no matter even whatever manifold you choose, they remain exotic. So recently the questions that now I am trying to work out is that now, as we see that I can only now talk about a single stabilization. So how do I, like, what is a way to find some kind of lower bound on such number? So like, as I say, how about two stabilization? Like, so a few questions is that, one, how to understand minimum number of stabilization. The second question is that when we talk about embeddings of 3 manifolds inside 4 manifold, so this is the smallest 4 manifold we can come up with, 2 copies of S2 cross S2. So a very interesting question would be, how do we construct exotic embeddings? Exotic embeddings of 3 manifolds inside in 4 sphere or CP2. This is I don't know. And you could also ask all family version of these questions. Like this is like just you can think of by embedding, I mean the pi naught. In the pi, that is what isotopy is. So you could ask what happens to the space of embedding. What is the pi 1 of space of embedding? What's the difference between pi k of smooth embedding versus topological embedding? And that is like one of my upcoming work, like which will be out in next couple of months probably. We are now writing, where we sort of shows that almost in all the higher dimensional homotopy or homology group, such kind of difference appear, that something which is exotic in nature. And this has some other relations with some other interesting problems like smell conjecture, which recently solved by Watanabe, but there is a case open which is whether there exists exotic diffeomorphism on 4 sphere or not. And this kind of problem also has some interesting relation with such problems. But I think I'm over time, so this is a good time to stop, and thank you.
So you made a statement that if you use 19 copies of K3, presumably that magic number is because it's B minus of K3.
Yes, that's right. And as I said, that this is I erase light bulb, but then you can do the light bulb trick essentially in that case.
And what happens if you, instead of stabilizing with S2 times S2, what if you stabilize with CP2 connected stuff?
Oh, then those are smoothly isotopic. That's right. So yeah, that's an interesting question. So there is another interesting property of S2 cross S2. I secretly hide the whole talk is sort of the spin nature. That is where this object appeared, spin to equivalent. So if I go to CP2 connected some CP2 bar, that property kind of not be useful. And so that's very interesting. And I mean, I wish I can give you an answer. I think we are still like a little bit away to answer maybe the question that what happened under connected sum with CP2 bar.
But there's, Bauer-Furuta in its primitive version still works even in the non-standard case.
Yes, but yeah, I thought a lot about it. I just don't know at this point how to do it, how to deal with it. But maybe, I don't know, maybe in future me or someone else could answer that question.
More questions? I was curious about that S3. Is that they connect something, or is this?
Yeah. So I didn't. Yeah. So this S3 actually you can get in many ways. As long as you decompose this 4 manifold into 2 4 manifold x1 connected some x2, where B2 plus so of each xi is 2, then this connected 3 manifold S3 has infinitely many exotic copy. So.
Oleg was wondering if exotic means that something is standard and then there are exotic copies.
Yeah. So that means this is the standard, and then you can build other copies which are not smoothly isotopic to this copy. Yeah.
More questions? Let's thank Anubhav again. We are going to go to